Welcome back, everybody. So let's continue exploring the logical model of HDFS, and we'll start with the physical layer. Some terminology, and actually that's also coming to some of the questions that were asked during the break. Key value model is a bit of an orthogonal concept. It's a mathematical concept. Basically, there is a key value model whenever you see a map or an associative array on the high level, right? So technically, Amazon S3 has a key value model. DynamoDB has a key value model. HDFS has a key value model. A file is the key, and then you have the list of blocks that is the value. JSON has a key value model, right? The attributes in an XML element have a key value model. It's basically everywhere. What you need to be careful about is that key value store has a very, very specific meaning. When you say key value store, people will understand it as this is DynamoDB and the like. It's really a system that is a very efficient way to get and put small values, no more than 400 kilobytes, in a very large distributed system. So when you say key value store, be very careful that it's really specific to that. But when I say key value model, this is really very, very generic. And in HBase, we saw that there is a key value model in the sense that the row ID is the key and the rest of the row is the value, right? In fact, we'll see a key value model somewhere else on the physical layer as well, but I'm not telling you too much yet, all right? Now, what you also need to be careful about is the notion, you probably, who heard about column stores or column storage, columnar storage? Okay. This is not to be confused with white column store. This is something else. Typically, in a relational database management system, if you store the contents of a relational table, this is done row by row, right? On the disk, the rows are together. Column storage changes the physical layer. It's still the same relational model, it's still tables, but physically on the disk, you store the columns together, meaning that all of the values in the same column will be next to each other on disk, and then at some other place, you have the content of another column. This is extremely efficient for the cases where you don't need access to all of the columns. Then it's very efficient with the input-output of the disk because you only need to read the columns you want and you skip the other columns. This is something you cannot do if you store row by row, right? Because then you would have to skip within each row, and that's not something you can do on the high level. For whom is that clear? All right, this is column storage, but this is not what we are doing today. We are not doing column storage. We are really doing wide column stores, which is this concept of column families that store several columns together. What we store together, as we will see when we look at the physical level, is the column families, right? I'll come back to that. The purple column family is stored together. The yellow column family is stored together. The red column family is stored together. This is the reason I said earlier that if you only look at one column family, it's a bit faster because you just ignore what is physically stored for the other families. This is one of the reasons. But accessing a single column isn't going to make it faster because the columns within the same family are still together. Okay, so these are wide column stores. And typically you can remember three names that belong to that family. It's Bigtable, which is the original, so the first one that was created. Apache HBase, that is an open source version that kind of is similar to Bigtable. That was released as part of, by the way, H is for Hadoop, right? It's the same as HDFS. It's part of the same suite. And Cassandra is, now it's called Meta, so that would be the Meta equivalent of a white column store. The design is a bit more different, but the ideas are exactly the same in the way that this is done, okay? Now, we are going to look at the physical implementation of a white column store. We are going to see how this is actually implemented on disk. And here, maybe something you might be wondering, because I told you already something on the physical level, I told you it's implemented on HDFS. The data is actually stored on HDFS. But now you might have a question in your head is, how come that HBase is optimized for updates and low latency, like you quickly get the values in the table and you can update single values, while I also told you that in HDFS, first, you don't have random access. It's not efficient to update a specific bit or sequence of bits within a block somewhere. Plus, HDFS is slow. It's high latency HDFS, right? You have to wait, like every time you type a command, you have to wait for 1 second and so on, right? So how can it be we manage to implement something low latency and random access on top of something that is high latency and doesn't support random access? Right, so this must be itching, and I'm going to, of course, give you the solution to that. Okay. Okay, these are the regions. This is the way we are going to partition the whole thing, because you know in HDFS we cut the files in blocks, right? These are called shards, splits, chunks, blocks. There's plenty of names. Well, here it's called regions. What is a region? It's an interval of rows. So we have to identify the interval, we identify it with a minimum inclusive, the first row ID in the region, and a maximum exclusive. So it's the first row ID not in the region. Why do we do that? It's just because it's very convenient, because then the maximum exclusive here is also the minimum exclusive of the next one, right? So this is why it's actually quite convenient to do things that way. Okay. Now, this here is the main message. We store together the intersection of a region with a column family. So what is in this rectangle right there, that is both partitioned horizontally with the rows and vertically with the column family, this belongs together. This is stored together. So this is why whenever you only access a specific region, or within a specific region, and not all column families, but just one, it's going to be faster, because physically, on the physical level, you only need to touch the data that is in there, and you don't even need to touch anything around, right? For whom does that make sense? All right, so this is stored together. This is the first big takeaway message today. We store together the data that is both in the same region, interval of row IDs, and column family. Next, the architecture. Well, guess what? It's exactly the same architecture as we saw in HDFS, meaning that we have this centralized architecture with a coordinator node called, it's not going to be called the name node, of course. This is just a reminder of HDFS, right? We had the coordinator is called name node and the workers are called data nodes. Well, here, the coordinator is called HMaster and the worker nodes are called region servers. So all you need to do is just learn by heart these two new words, HMaster and region server. But again, in your head, this is to be compared with name node and data nodes. Okay, so you have two new names to learn. Okay, something else that I should say here. I mentioned, even though I didn't insist back then, that when we say name node and when we say data node, we kind of abuse the language by calling the nodes that way. Like the machine, this is the machine that is the name node, this is the machine that is the data node. But if you want to be precise, these are processes. The name node is a process running on that machine. The data node is a process running on that machine. But there can be other processes running on the same machines. And in fact, HMaster is a second process that runs on the same machine typically as the name node. And region server is also a process that runs on the same machine as the data node. And why that actually makes a difference in performance, we will see. The fact that the region server and the data node are two processes running on the same machine, and as a consequence, reading from the same local disk is going to be a huge difference in terms of performance. But I'll come back to that. Okay, so let's start with the HMaster. So it's kind of intuitive, just like the name node is doing the metadata stuff, like creating a directory, deleting a directory, and so on. Well, the HMaster does the same thing. It allows you to create a table, to delete a table, to add column families, and so on and so on. So data definition language operations, right? Second, the HMaster assigns the regions to the region servers. This means that, you know, this is like, by the way, I think of it as a big cake. Imagine that this is a big pie or a big cake, and you just cut it like vertically and horizontally to share it with your friends. It's exactly the same thing here. So in that case, we look at the horizontal shares of the big pie, and every one of the regions is assigned to a specific region server. This region server right here is responsible, excuse me, for this region right here and this region right there. When I mean region, I mean all the column families in that region, right? We'll see that physically it's going to be stored apart from each other, the column families on the disk, but in terms of responsibility assignments to the region servers, you assign the regions, the entire regions. You never have two column families of the same region that would go to do different server. That never happens. An entire region always goes to a region server. Okay, so this is the assignment of the regions. Next, you might, when you add and add and add and add row IDs, you might have what's called the hotspot. It means that you add a lot of rows in the same location. They have very close row IDs to each other. That means that a specific region that is defined by a minimum and a maximum row ID might grow a lot and become very big. In that case, what you do is that you split it into two regions. They stay on the same, when you do that, they stay on the same region server, these two, but you just split it. And then what you can do is reassign the responsibility. Then you can move away the yellow region here from that region server and say, okay, now you're no longer responsible for that region. It's this machine here that now becomes responsible for this region, right? So again, there's two different things that happen here. The first one is splitting a region that in itself doesn't move anything. It's only a logical thing. And then moving around the regions. That's actually rebalancing. You can also rebalance maybe because you might have a region server that crashes or goes away. Then you just reallocate the responsibilities to other region servers, right? This is all done by the HMaster. So it handles the failovers. Okay, for whom is that clear? Okay, now let's look at the region server. I'm going to say something else that is very important to understand. A region server is not responsible for storing data. That's HDFS. We are going to see it's all stored in HDFS. So it's not responsible for the persistency. It's responsible for serving requests, meaning that if a user comes and says, I want the data for that region, then the region server is responsible for taking that data from HDFS and serving it to the client. What you need to understand is that all region servers have access to the same HDFS. It means that technically all region servers see all the data that is persisted in HDFS, right? This is very important to understand because this is the reason why you can so easily move over the regions across machines, right? This is the reason, because they all see the entire HDFS. Okay, now, this is the challenging part that is coming now. So again, this is why I put you the warning so that you don't worry too much, but we'll take the time to go through it. We have half an hour and then we'll continue tomorrow, but don't hesitate to ask questions if anything is unclear. We've already established that the way that we partition the data is with this pie cutting thing that we both cut horizontally and vertically. And every intersection of a column family here and of a region there gives you 1 unit of storage, which we very originally call a store. Okay, so it's a store. Now, if I look inside a store, so first, as a reminder, a store is one specific region, a continuous interval of row IDs, and it's only one row column family. So now there's no other column families than this one in a specific store. What is there within a store? Well, then there's the cells, which are the individual values that are stored with HBase. So what is every cell? It's basically the intersection of a row ID and of a column name, right? So the row ID is within the region of the store and the column name belongs to the column family of the store. Well, again, I'm abusing, I have to be careful because that's maybe why you were confused earlier. when I say the column name belongs to the column family, I should be more careful. What belongs to the column family is the column that is identified with the column family plus the column name. You could still have the same column name used somewhere else, but again, it's like two people having the same first name, right? Just saying it again, closing the parenthesis again. So one column, one row gives me one cell. It's the equivalent of a cell also in a relational database or in a spreadsheet software if you want. So this is a cell. Now, what happens is that all of the cells, so the values that are in the cells, are going to be persisted somewhere. It needs to be stored somewhere so that even if we shut down electricity, it's still there. The way that this is done is files sitting on HDFS that we call H files. H again for Hadoop. A lot of things start with H in Hadoop. So this is an H file. So the cells will be stored as 1 or 2 or 3 or more H files on HDFS. What's inside? We'll also come to that. We'll also show you what is inside and how they look like. But the idea is that you can view an H file as a sequence. Guess what? The key value model is back, right? So every H file is just a sequence of key values. So what happens is that every cell that is in my logical table, this is the logical view of my region, my column family, I have here a cell that corresponds to A1, right? So this is row ID A and column name 1 within some column family. It's going to be stored right here in the H file where I have here A1. This is on the left, I have the key, so that's A1 plus the name of the family, but it's the same everywhere. And then here I have the value that is stored in there. Then I have, let me do it in that order, B1 that is stored there. I have C1 that is stored over there. I have A2 that is stored here. I have B2 that is stored right there. And I have C2 that is stored there. Now you notice that these key values are sorted. Because if you look at the way that the keys are sorted, it's A1, A2, B1, B2, C1, C2. So there is an order, and this is all alphabetically sorted. So in an H file, you have a sorted list of key value pairs. They are all sorted by key, right? So this is what an H files look like. Furthermore, I'm going to throw in one more thing. You might have multiple versions of the same cell coexisting. All it means is that you expand the key to not only have the row ID and the column family and name, but also a version. So you have basically here a key value that says this is version 1 of cell A1, this is version 2 of cell A1, this is version 3 of cell A1, and this is version 4 of cell A1. Of course, one of these is the latest, right? When you look at them, you know that version 4 is the latest one, okay? So an H file is a sorted list of key value pairs, and the keys contain the row ID, the column family, the column name, and the version. And again, I'll repeat it with another slide after that. Who is following? Okay. Now, you notice that when I talked about the versions, I'm using integers, 1, 2, 3, 4, and so on. Yes, go ahead. The catch box over there. Yeah. Oh, wow.
Can you go back to the previous slide? I noticed that on the first row, there's actually a blank row. Is that metadata? Store the row ID somewhere within this H file? Brown one, yeah.
Let me try to maybe if I move here. So do you mean here?
The first.
Oh, here.
Row. Yeah.
Oh, this is only for the probably because I love relational tables, so I couldn't help adding a header. It's only logical actually. This is not actually stored. This just means that this is the key and this is the value. Maybe I should remove it. It would be less confusing. That indeed might confuse more than it helps.
Okay, thanks.
Thanks for the observation. That's always a way to improve further the slide. Okay. All right. So now the versions that I'm showing here are integers, meaning that it's a total order, as opposed to a partial order. Where did we see a partial order? In DynamoDB with the vector clocks. In vector clocks, we saw that it's a DAG, directly the cyclic graph. Why? Because we can have conflicts in DynamoDB. It's not consistent, it's eventual consistency. So we might have differing versions at the same time of the same cell. But we don't do that in HBase. In HBase, it's consistent. We always have a single latest value of every cell. So you could, if you want to have a shortcut in your brain, total order means consistency. You have a latest version. Partial order, DAG, means eventually consistent. You can have conflicts that you need to resolve. In HBase, we have an ordered total order on the versions, and there is a guarantee at the row level of acid, so of the fact of atomicity, let's say, right? You cannot modify concurrently the same row by multiple users. You basically lock the row when you are touching it. This is how you ensure that the versioning is going to be linear as opposed to a DAG. For whom does that make sense? Very good. Okay, and by the way, this idea of total order, consistent, partial order, eventually consistent, that's a general take-home message that is valid at plenty of places in computer science, right? So one way of achieving consistency is to have a total order on the versions. Yes, there was a question. I saw a raised hand. Yeah. What is mean? So let's dive in more details here. So when we look at the versions here, I was speaking about the versions of a single cell, right? A single cell. What is new here at the bottom of that slide is that we could have said, okay, I can have Alice modifying that cell and Bob modifying that other cell in the same row, right? We could have made the design like that. But atomicity means that it has to do with the serialization of transactions. It means that Alice has to wait until Bob is done in order to modify a cell on the same row, right? Now, the connection with the fact that it's binary, can you maybe elaborate on the argument for the binary part?
I thought atomicity meant that was...
Yes, get it. Now I get it. So this is a collision of terminology. This is what's happening here. Atomicity can mean two things. There is atomicity in terms of the first normal form, that a value is atomic and you cannot have nested values, a table in a table. That is atomicity for the normal forms. And then there is the notion of atomicity for transactions, in the sense that a transaction is entirely executed before another transaction is entirely executed. So I'm very glad you make that point. That is super useful and it clarifies for everybody. There are two notions of atomicity that are not the same thing. It's the same word. These are two things. For whom is that clear? All right, so atomicity normal form and atomicity for transactions. Thank you very much. That was really a good observation. Yeah. Okay. So now I'm just showing more details of what I've already been telling you, is that we are storing these key values, right? So this is a key value model. But of course, by the way, these are the two headers that I added. Now they are no longer covered, right? Key and value, that clarifies. But basically, when you store data on a disk, it ends up as a sequence of zeros and ones. That's what you see on the disk. It's a bunch of zeros and ones. So this table here, it's just because us humans interpret it in that way. But on the disk, what you're gonna have is just a bunch of zeros and ones that are a key value, followed by another bunch of zeros and ones that are the next key value and so on, right? So this is how it's stored eventually on disk. And that actually causes a few challenges, mostly because the length of the key values might be different every time. And when you have to write key values of different length, the challenge is to know where they start and when they end, the key values. This is not easy at all. So there is a trick, actually, is that whenever you store a key and a value, you also store the length of the key, so the number of bits or the number of bytes, just a matter of convention, the number of bytes of the key and the number of bytes of the value, and then the key and then the value. Now you could ask, okay, how do we know the length of the key length and the length of the value length, right? It's like the Baron of Munchausen, right? The bootstrapping thing. Well, the key length and the value length are fixed size. This is going to be typically 32 bits, and that's it. So that you know that it's exactly 32 bits. And once you have read the key length and the value length on 32 bits, then you know how many bits to read to get the key and how many bits to read to get the value. This, in fact, is called a prefix code, when you can actually do that, because you know when it starts and when it ends. Who took information retrieval? Okay, so for you, I have something. I don't know if the others will know, but this is just to put it in perspective with the gamma codes. When we have the gamma codes, it's an encoding of integers that has the property that you can tell when it starts and when it ends. For example, here, if I decrypt the numbers with the gamma code and so on. So if you never saw that, don't worry, just consider it as magic, right? You know that any sufficiently advanced technology is indistinguishable from magic. So this is just magic. And what it does is that it's listing integers and it magically tells you where that starts and where that ends. And one technology to do that is called the gamma code. Well, in fact, we are doing exactly the same thing with the key values by storing the length every time. And by the way, just to make the connection, where is the length in the gamma code? How do I know the length? Let me tell you that was the last semester. It's the number of ones. You see all the string of ones tells you exactly how many more bits to read there, right? Here you have 2 ones, so it's 2 bits. Here you have 3 ones, so it's 3 bits. It's exactly the same concept as when you have the length. Okay. So key length, value length, the key that is elastic, and the value that is elastic. Now we are zooming in on the key, right? We're just looking at the key. So what is there in the key? Well, that shouldn't be new to you because I already told you in the key, there is the row ID, there is the column family, there is the column name, column qualifier, and there is the version, right? This is what we have in the key. So that shouldn't really surprise you in here, what you see, right? The key, the family, the qualifier, the timestamp, this is actually the versioning. The last one could come as a surprise. It's basically just a bit to mark as deleted or not deleted, right? So it's very convenient to, we'll come back to that when you delete stuff. Okay, now we still need to make sure to deal with the elasticity because the row can also be elastic. We don't know the size of the row ID. The column family can also be elastic, right? The column qualifier can also be elastic. So all we know is the total size of that because that was given by the key length that was given earlier. But now what we need to store is also the row length, so the length of the row ID, right? So this is also fixed, so let's say 32 bits, and then you know how long that is given that. Then you store the column family length on a fixed size, then you know how long that is. The timestamp is fixed. It's also a fixed length thing. This is just 1 bit or 1 byte. I'm not sure if it's 1 bit or 1 byte, so hope you forgive me on that, but this is really a detail. Why don't we store the column qualifier length? Yes, go ahead. Can we throw it behind you or beside you? Yep, over there on the front. Here. Yeah. Oh, wow.
Well, because we can infer it. We know everything. We know length of everything else. So why should we store this?
Exactly. So it's a subtraction, right? You just subtract all the known length from the total length, and what remains is the length of the column qualifier, right? So if we had added the column qualifier length, that would have been redundant, basically. This is why we don't have it. Yes, go ahead.
Seeing now that we have a timestamp, I suppose that's a sort of time of update or modification or insertion. I know that usually time is a very complicated thing to synchronize across clusters. Mm-hmm. How does that work here to achieve consistency?
That's a very good question. Actually, you push me to my limits because these are the parts of HBase that I would know less about. Let me tell you the little that I understand about the way that versions are handled. Technically, the versions are part of the API in the sense that as a user, you can control the versions. You can force when you write, when you put, and so on. You can supply your own version and have full control of what is written in there. If you don't, and if you add stuff, that HBase will add one for you. And this is where you push me at my limits because I don't know. Basically, the reason that I'm saying I'm pushed at my limits is that I explored, of course, all of that, trying to understand. I saw two contradictory or seemingly contradictory things because first I would have understood as you that you use the current time or something to give you the timestamp. But there is also somewhere else a parameter in HBase that gives a hard limit on the total number of distinct versions you can have. And the two things contradict each other. So this is the part that I haven't fully figured out yet. Right? If you can, or if somebody investigates and knows more, I would be interested in that. But this is really, for me, pushing me at my limits on the internals of the timestamp.
Okay,
right? But this is great because this is how we learn, right? Yeah. Any other questions? Okay, so this is the key. All of that. This is the key. And these are really just bits, the sequence of bits. Okay. All right, now there's more. Because we have a very large sequence of key values that are stored in my HFile. Now we would like to have a way to quickly access them. So they are sorted, right? So you could think, okay, let's do a binary search. Yes, but it takes a bit of time to do a binary search. So what we do on top is that we also use a block system within the HFiles that groups in 64 kilobytes blocks of key values. Big warning. It's exactly like the atomicity earlier. When I say block, I don't mean an HDFS block. This has nothing to do with the HDFS block. So of course, this is HFile, it's stored on HDFS. So of course, there will be HDFS blocks. Here, this is different. These are blocks within the file as it is used by HBase that is grouping the key values in 64 kilobyte blocks. For this reason, I made up that terminology of H block. It's not official, but if I call them H block, it clarifies that this has nothing to do with HDFS blocks. That's the reason, right? Now, something also that you need to understand, and this is also a difference with HDFS blocks. For an HDFS block, you count 128 megabytes and then you cut. That's the end of the block. So you just count the number of bits and bam, that's the end. Here, you never, ever cut in the middle of a key value pair. Never. So it might be that if the end of the 64 kilobytes would be in the middle of a key value pair, you just continue all the way to the end of the current key value pair. So it might be that a block is larger than 64 kilobytes, right? In fact, since I told you that a value can be as large as 10 megabytes, you could have H blocks of 10 megabytes, right? Just because you have a value that stretches it all the way, right? But if you have plenty of small values, then that's going to be 64 kilobytes, okay? So what do we do? Well, in the H file, we have an additional auxiliary structure, that's kind of an index, that helps reading it faster. This is a structure that is also stored as part of the H file that gives you the starting keys of every H block. So it tells you key 1 starts the green H block, then key 5 starts the yellow one, key 11, the orange one, and so on. What happens is that this is all stored in the H file, so it's all stored on HDFS, but when you want to read it and access the contents, the first thing you do is that you copy over the left part, so the actual index, you load it in the RAM, in the working memory, all of that. It's small enough that you can do that. So that you load in the RAM. Once you have loaded that in the RAM, it's straightforward to navigate the structure right there. For example, you look for key 14, okay, it's between 11 and 17, and bam, there you are. Then you know that you specifically access that part of the H file, sorry. And this is where you find key 14 in that block right there. Does it make sense? Yes?
But I suppose we still have to read through key 11, 12, 13 to get to 14. Like we can directly access key 14, even though we know it's between 11 and 17.
I didn't get, sorry.
If we look for key 14
Mhm.
and we know it's between key 11 and 17,
yeah,
we are not going to directly access this. We still have to.
Oh yes, absolutely. So here I was a bit quick. If it's that way, it's probably a binary search. Well, it's actually so small that I don't even know if a key value search, even if a full scan, that's actually a good question. Either it's a full scan if it's fast enough that you don't even care, then you just do brute force, or you do a binary search, or you build if you put that in tree map, for example, then you can efficiently retrieve that, right? So I think these are actually very interesting details, right? So when you load it into memory, you can build the additional structures of lookup, but it might also be that the structures are pre-existing and also stored on disk. That's actually a good question and also a nice thing to investigate to know more how it's done, right? Okay. But this is a good question, right? I thought right away as a human key 40 is here, but of course it requires a bit more work than that. You still need to figure out how to look it up. Okay. Okay. By the way, we'll come back to that sort of indices in the document store course, because we look into B+ trees, into hash indices and so on. So we'll spend a lot of time, not specifically on HBase, but on how to build index structures, right? So there is more to come on that. Okay. But I still, if you could mark, just if you want to be my memory, Matt, that you take a note, if I can investigate that, maybe I can find out more about the exact structure of the index there. Right. Sometimes it's not easy, you know, when we do this kind of investigation, because there's the original paper, basically. So in that case, HBase, there's also Bigtable. They might not have done it in the same way. So sometimes they do it differently. And sometimes it's not even in the paper. Then you could think, okay, where is that? Well, it's in the code, right? So I could start looking at the code and try to understand how that works, but this doesn't scale. But what usually happens is that some of the engineers in the team, so be it HDFS, be it HBase and so on, sometimes posted on internet forums some explanation that is not in the original paper. And so if you search hard enough, sometimes you find posts like that by engineers that give you that level of details. And this has a lot of value. Unfortunately, it's not done for everything. So there are questions that remain without answer, but sometimes you find that kind of jewels on the internet. Okay. Okay. Now I'm continuing to give more and more details. I have 5 minutes left, so I'm just going to give you this hierarchy, and then we'll stop there and continue tomorrow, because as I said, it's a lot to digest. So what are the levels of physical storage? I'm going to give you a hierarchy here. We have the entire table, right? With all the rows and all the column families. Inside that table, we have the regions. This is when we cut horizontally, right? If we cut horizontally, we have regions that are intervals of row IDs. Next, we have the stores. That's the vertical cutting of the regions, where we cut by column family. So several regions per table, several stores per region, one per column family. Within a store, I have multiple HFiles, right? I can have my key values within a specific store in multiple HFiles. How can it be it's multiple HFiles? This is something I haven't told you yet. In fact, we'll see tomorrow how we actually can land with multiple HFiles, how that is. I keep that as a cliffhanger. But basically, it can be stored on multiple HFiles. Within an HFiles, we saw that they are stored in these 64 kilobyte H blocks. And within the blocks, we have the key values. Does this hierarchy make sense to you? For whom does that make sense? Okay, so this is how to think of it if you want to order things a bit in your brain. Several key values in an H block, several H blocks in an H file, several H files store the data for a store, several stores across the column families give you a region, and several regions give you a table. That's how I order things in my brain, okay? And now the cliffhanger I'm leaving you with is that the problem is when we write to HDFS, we can only write a single file at a time and then append thing. We cannot modify in place. There is no way we can update that in place. So how can we deal with that? That HBase is a system that people constantly add stuff to, And yet, when we add on this, all we can do is append. How can we insert new values? So that's the big question I leave open for tomorrow before I just check how much you followed. Please just first answer this question here. Just checking. So tomorrow I'll take the time to answer any questions that pop up, but also you will get many answers tomorrow because I'll continue to give you more details. And you'll see at the end, things will just add up, right, in the whole working system. So let's see what we have here. Okay, as I told you, it's tougher than usual. So that's expected that it's a bit lower, but we still have a majority above 80%, which is great. So thank you very much, everybody, for joining. I'll see you tomorrow at 9 a.m. for the continuation. Bye.